Eldar Rubinov. So Eldar, please feel free to take over the screen sharing, and I will introduce you quickly. So Eldar Rubinov is the positioning, navigation, and timing and geodesy technical lead at Frontier SI, a not-for-profit research organization in Australia. He holds a bachelor's degree in geomedic engineering and a PhD in high-precision GNSS positioning from the University of Melbourne. Before joining Frontier SI, Eldar worked in various industry roles, eventually taking on the role of technical manager for the Australian and New Zealand SBS testbed. He now leads the organization's PNT portfolio and is currently establishing PNT Labs, a dedicated testing and evaluation facility designed to assess the performance and resilience of navigation and timing technologies, including LEO PNT. And with this, thank you, Eldar, for sharing your presentation with us, and the stage is yours.
So much, Marcus. Welcome, everyone. I'll also say good evening, good morning, and good afternoon. I'm based in Melbourne, Australia. It's 11 p.m., so it's very much into the good evening territory. So I'm going to do a presentation called Navigation in the 21st Century. So it's going to be an overview presentation to set the stage for some other more technical talks. So, yeah, let's see. Okay, so that's the presentation outline. I'm going to briefly talk about navigation, the rise of LEO PNT, talk over some of the technical aspects, some space and receiver segments, and then of some service providers. Okay, so let's firstly talk about navigation. What is navigation? You can see I've pulled up some definitions of navigation from various agencies. They're all more or less similar. It's all really about getting from A to B, but in some cases, like aviation, for example, there's some very strict performance criteria and so on. Now, there's various modes of navigation. So you can be walking, you can be in a car, you can be on a train, on a plane, on a ship, and so on. Every domain is different and requires certain characteristics. So if you're in a car, for example, you can only move in two dimensions. You can't go up and down. If you're on a train, you're really kind of on one line, so you can only go forward. And that's why you need to each of those domains has its own characteristics that you need to take into account. Now, how did we used to navigate in the old days when we didn't have satellites a couple of centuries ago? Well, we used to use things like celestial navigation. So, for example, using sextants to make measurements to celestial bodies. You can actually compute latitude very easily. And if you had a good enough clock or a chronometer, and at this time you used to do it at sea most of the time, you can actually compute your longitude. And if you're interested in that topic, I can recommend a very good book called Longitude, which talks about the navigation back in those days. Also things like dead reckoning, which is estimating your current position based on your previous position. And then as we moved into 20th centuries, we started to use radio navigation. This was still before satellites. So we used to things like LORAN, long-range navigation. So it's a radio frequency signals from ground stations, and also things like VHF omnidirectional range, which is still used in aviation to this day. And then, of course, came the satellites. GPS was the first, and then it was followed by other global navigational satellite systems. And that's completely revolutionized navigation. So the ability to compute precise position and time on or near the Earth's surface 24/7, regardless of the weather, it has completely revolutionized how we navigate, and it's still very much a backbone of modern infrastructure. It's used for many critical infrastructures, for timing synchronization, it's used for navigation, and it's also used for positioning. So if we have GNSS, why do we need other things like LEO PNT? Well, it turns out that this day and age, GNSS by itself is not enough. As good as it is, GNSS does have some drawbacks. Mainly, the signals are extremely weak. They're coming from satellites that are 20,000 kilometers away, and by the time they reach Earth, they are weak and they're vulnerable to radio frequency interference, such as jamming and spoofing. And today we see many instances of that happening all over the world, especially in the conflict zones. I put a couple of examples there, and this is all just in the last couple of months, a few months. So there was the ship crash offshore of UK in March, and then there was also a plane crash in December, which that plane was shot down. But before it was shot down, it was actually jammed quite heavily, which led to it crash. Now, so in the 21st century, navigation is going to be more than just GNSS. GNSS is still going to be probably the primary method. It's not going to go away anytime soon, but there's many other domains that are being worked on. So LEO PNT is obviously the topic of today's webinar, but there's also terrestrial broadcast systems, there's inertial navigation systems, visual navigation and SLAM. There's a lot of work going on in quantum navigation, magnetic map matching. Celestial navigation is actually making a comeback. It's something that's from, as I said, a couple of centuries ago, but it's actually being used in some cases today as well. But of course, the topic of today's webinar is LEO PNT. So let's start. Let's put our attention to that. So LEO PNT is a disruptive technology. We started looking at LEO maybe a few years ago. It's found its way onto navigation stage. Due to those reasons that I mentioned before, so just because GNSS started to have those vulnerabilities. And we knew about those vulnerabilities a long time ago, but it's really now with all the conflicts that are going around the world that those vulnerabilities are really starting to show. Interestingly, unlike GNSS, which is operated by governments, LEO PNT is largely driven by market demand. So it's, in some cases, it's governments, in other cases, it's actually private companies who are doing this. Now, so Frontier SI is actually about a year ago, we started doing a project with an Australian company called Skycraft in LEO PNT, which was funded by the Australian Space Agency. And when we started that project, we kind of thought to ourselves, well, what is actually happening in this space? What is everyone else doing? So before we wanted to do anything, we wanted to understand the landscape. And what we realized is that there are many different initiatives going on, and there's a lot of noise, and it was really hard to just gauge what is everyone doing, what are the differences, what are the similarities, and things like that. And there wasn't really anywhere like a report or a document that sort of went over that and explained everything in detail. So we thought before we start doing anything, it was a good idea to compile such a document, which we've done. We released it earlier this year in January. We called it the State of Market Report on LEO PNT. And we actually went through the ecosystem, went through the market. We looked at all the players, we looked at the technology, and we really broke it down. We called it 2024 edition because we realized very quickly when we started working on this is that the ecosystem is moving so rapidly is that any report that you're going to do is going to be out of date almost as soon as you release it. So what we've done, we decided to do the 2024 edition, and we're going to repeat this report every year for the next few years, and we're going to monitor the growth of the ecosystem. Now, there's actually different ways that you can do PNT from LEO, as you can see on this slide. So there's three main categories. First, you have dedicated constellations. So this is where you design and launch a constellation with the primary purpose of doing PNT. So just like GNSS, but in LEO. Because it's in LEO, you're going to need much more satellites to have the same coverage. So GNSS systems typically have about 30 satellites in medium orbit. With LEO, you're going to need anywhere between 200 and 500 satellites. So it's typically aimed at high accuracy applications. It complements GNSS in a number of ways. It's mostly in L band, which is the same band as GNSS, or in C band, and I'm going to get to that in a few minutes. So I showed a few examples of different companies that are working in each of those columns in each of those ways. Some of them actually it's very gray. You can put them in different categories. For example, that's why you see some of them in different categories. The next way on how to do LEO is by using signals of opportunity, and we're going to have a couple of talks today from Zach and Winfried on that. But essentially, it's using signals from satellites that are not designed for PNT. So something like Starlink, for example, is a prime example, because any satellite that transmits a signal, whether it's for communication or something else, it's still a radio signal. So you can use it, you can extract a Doppler shift or pseudo range or carrier phase range, and then if you can do it, then you can actually use it for navigation. It's very different because you don't know the design of the signals. The signals are mysterious, so you have to decode them yourself. They're not really designed for PNT. There's large orbit and clock errors, but there's a lot of work going on in that area, as again I'm sure we're going to hear a bit later today, and some trials are actually showing that meter level positioning is also possible. And the last category is fused or integrated communications and PNT systems. So again, there's many different SATCOM constellations that are going up. So Starlink is a front runner, but there's many others that are just starting. And any satellite communication system can also be used for PNT should the company decide to do it. Okay, now let's start looking at some technical aspects. So satellite frequencies are the fundamental thing that we need to understand. So most satellite signals are in that sort of super high frequency range, which is from 1 to 40 gigahertz. It's broken into a number of different bands. We got the L band, S band, C, X, KU, K, and KA bands. GNSS mostly sits in the L band, which is between 1 and 2 gigahertz. You can see all the different GNSS signals, with just one exception from NAVIC, which is an Indian regional navigational system that has one signal in the S band, most of the others are in the L band. C band, which is the band between 4 and 8 gigahertz, was also considered for the use of GNSS in the early 2000s, but it never eventuated for different reasons. But we're going to see that now, 25 years later, C-band is actually going to play quite a large role in LEO PNT landscape. Very quickly, I'm going to talk about some technical, I'm just going to briefly mention some technical aspects between GNSS and LEO PNT. So precise orbit determination is one of them. And again, there's going to be a presentation from Amir on that. So I'll just very quickly just say that the biggest differences between GNSS and LEO PNT is, of course, the orbital altitude. With GNSS, it's roughly about 20,000 kilometers. With LEO PNT, it's anywhere from 500 to 1,200 kilometers, which means that with GNSS, your typical horizon pass is anywhere from 6 to 8 hours, but for LEO PNT is 5 to 15 minutes. So it's highly dynamic, and it also subject to many significant non-gravitational forces that need to be taken into account. Timescale reference is another fundamental aspect. So timing is everything. So positioning and navigation both depend on precise timing. With GNSS, timing is easy. Every GNSS satellite has 4 atomic clocks, and they get frequent updates from the ground stations. But for LEO PNT, you cannot have atomic clocks. They're too heavy, they're too expensive. You need far too many of them. So on LEO satellites, you typically use much cheaper clocks, like the chip scale atomic clocks or oven controlled crystal oscillators. They drift much faster, so you need to be able to update them more frequently. And there's different ways you can do that. You can have the first one you can see here, you can have many different ground stations. So you can update the satellites directly from the ground stations. The second way is probably the easiest one. You can just use GNSS satellites. If you have a GNSS receiver on your LEO satellite, you can actually use timing from GNSS or even geostationary satellites like SBAS satellites, for example. That's the most convenient and most easy way to do it, but the problem is that is your LEO constellation, in that case, it's not really independent from GNSS. So if something happens to GNSS, it's also going to affect your LEO constellation. And another way to do it is by using optical inter-satellite links. So some satellites will still receive updates from ground stations, but then they can synchronize the time between different satellites using optical links. Ionosphere presents the biggest kind of difficulty for radio navigation signals passing through it. With GNSS, again, we know how to deal with it. Again, it's just the signal that passes through it, and because we have multi-frequency and ionosphere is frequency dependent, we can do different linear combinations and we can deal with the effects of the ionosphere that way. But with LEO, the satellites themselves are actually inside the ionosphere. So if there's any events like scintillation or plasma bubbles, it might actually affect the satellite in a bigger way, so which will require some more resource intensive signal processing to deal with it. And finally, resistance to RF interference. That's a major driver for LEO PNT. Because the satellites are so much closer to the Earth, their signals are much stronger, so they are more resistant to jamming, to interference. The diverse use of frequency bands, it's also important because with GNSS it's just L-band, so most of the jamming and spoofing also happens in the L-band. In LEO, we can actually use different frequency bands which are less congested. And also, because we're designing the systems from scratch, at least the dedicated systems, we can have some advanced signal design and security features in those systems, which we don't have in GNSS. And the thing is, GPS has been around for more than 50 years, so we have a lot of experience of using GPS, of some of the hurdles, of some of the difficulties with GNSS, and we can incorporate all those lessons when building new LEO systems. Now let's talk about space segment aspects, which are also very important when you're designing and launching a LEO constellation. So launch cost is a very important factor. It typically is about a third of all costs associated with your constellation. And it was interesting, so from 1960s to about 2010, the space launch costs haven't really changed much. There was a bit of stagnation. But since SpaceX came along, it's really democratized the launch and enabled large amounts of LEO satellites to be launched into the orbit. So that was one big factor that led to many of those systems being developed at the moment. Satellite platform itself is another very important consideration. So there's different classes of the satellites, from small CubeSats, nanosatellites, 1 to 10 kilograms range, to microsatellites, which is up to 100, and mini, 100 to 500. And bigger. So for LEO satellites, we see that micro and mini, so 100 to 150 kilogram satellite range, hits that sweet spot where you can have dedicated PNT payload, but it's still small enough to be launched in large quantities. But we also see that some companies choose to go down a much smaller, so like a nano satellite, so 10 kilogram CubeSats as well, where we're also seeing that. Constellation design, that's another very important consideration. So what type of orbits you want to have in your constellations. There's different types of orbits. There's polar or sun-synchronous orbits. Then you have mid-inclination orbits. So with polar orbits, you actually have better coverage at the polar regions, but not such a great coverage in mid-latitudes. With mid-inclination, it's the opposite. You don't have good coverage at the polar regions, but you got good coverage in mid-latitudes. So you can choose which orbits to use. You can have combinations of different types of orbits, depending on the coverage that you want to achieve. How many satellites in view do you want to have, which will also dictate the performance that you're going to get out of your constellation. And receiver segment is also very important. So fine, you can launch a constellation of satellites which are going to transmit signals, but if there are no receivers that can receive those signals, well, there's not going to be much use for it. Currently, all current GNSS receivers are in L-band, and the LEO, again, most of the dedicated constellations are either in L-band. If they're in L-band, it's very easy to incorporate into current GNSS receivers. In some cases, all you need is just a firmware upgrade, and then you can start using those new signals. If it's in a different band, like a C band or an S band, then you will actually need to have an entirely new receiver. So there's new business models with the receiver manufacturers that need to make decisions about what sort of receivers to invest in, how to partner up, who to partner up with, and so on. There's a lot of market dynamics that are going on. Now let's look at the providers. So when we did our report, we found there's 9 dedicated LEO PNT service providers that you can see on this screen. I'm going to quickly go through all of them. What we did in our report is we tried to come up with a set of common characteristics so that you can easily compare between all these different providers. But before I'm going to talk about those, I'm just going to throw back for a second to Transit, which was the original LEO PNT that was developed by DARPA and Johns Hopkins Applied Physics Lab in the 60s. It consisted of 36 satellites in low Earth orbit. Because it was a very small number of satellites, you could probably only see one satellite at a time, so which meant you need to track that satellite for 10 to 16 minutes, and usually you would do it for maritime applications, so you would be on a ship, and it would take that long to essentially get a position fix. And the typical accuracy you would get was between 27 and 37 meters, which today it doesn't sound like much, but back in those days that was actually quite significant. It was on the only satellite navigation constellation available, and it was used widely by thousands of ships until the 90s when it was superseded by GPS. Now, if we very quickly, I'm not going to spend a lot of time talking about each of those service providers. I've put the information on the slides. The slides will be available. But as you can see, we put those important characteristics about each of these constellations, which you can look at. It's also in our report. But very quickly, Iridium STL. STL stands for Satellite Time and Location, which was originally done by a different company called Satellus, which used the Iridium constellation of 66 satellites and actually had a hosted navigation payload on those Iridium satellites, and they delivered the STL service. And last year, I think Iridium has actually taken over Satellus, so it's now one company. It's called Iridium STL. It's the only commercial LEO PNT service that's available at the moment. They have a number of receiver partners. Because it's 66 satellites, which is quite a low number of satellites in LEO. It's also in a polar orbit, which means you can, again, you probably see 1, maybe 2 satellites in most mid-latitudes. But in the polar regions, you see quite a lot more. So for timing, it's perfect because you only need 1 satellite for timing, but for positioning and navigation, it's not optimal. So that means you can do high precision positioning at sort of sub-meter level, let's say, and the typical accuracy you can achieve is about 10 to 20 meters. Next is Zona Space. So Zona is a startup, a US startup, which was founded in 2019. It's developing a dedicated LEO PNT constellation called Pulsar. It's going to have 2 signals in L-band, so which means it's going to be compatible with many existing GNSS receivers. It's aiming at high accuracy, centimeter level positioning. Next is TrustPoint, another US startup which was founded a year later. TrustPoint, unlike Zona, they're actually doing it in C-band, so they have a signal a single signal in C-band. It's also aimed at high accuracy sub-meter decimator, potentially even better than decimator applications. But they're using C-band, so it's two different ways to go about it. There's no really right or wrong way, but it's interesting to see how different companies and what their strategies and philosophies are. Another interesting thing about TrustPoint that they're using very small satellites, so 10 kilogram 6U CubeSats. Next one is JAXA, so Japan Airspace Exploration Agency, are also developing a LEO PNT constellation. First phase 240 satellites by 2030 and second phase 480 satellites by 2035. They're also using C-band like TrustPoint, and the aim is really to augment GNSS. Okay, I think in the interest of time, I'm just going to skip through that pretty quickly. Arcade Space, another Japanese startup, they're working with JAXA on the JAXA's constellation, but they're also doing their own constellation for maritime called VDES, which is VHF Data Exchange System. So it's a communication system, but it also has a ranging component to the positioning. In China, there's at least three constellations that are going up. So Centispace is the first one. Again, dual signals in L-band, so similar to Zona. Geely is another one. It's actually an automotive manufacturer, so it owns brands like Volvo, Zeekr, Polestar, and some others. And they actually established a G-Space, which is a SATCOM communication company, which is going to have in excess of 5,000 satellites for communication and also have a small subset of those for PNT. And the last one from China is called SatNet Leo, which is owned by China SatNet. Again, they're doing a mega constellation for communications, and they're going to have a subset of those 500 satellites for PNT. ESA are doing an in-orbit demonstration. At the moment, I'm not going to talk too much about that because we have, again, a presentation from Rusan Nadas, who's going to talk about that in more detail. And if that wasn't enough, there's actually two more LEO constellations, one out of Turkey, the other one's out of UAE. They're very new. There's not a lot of information, only very little information on each of their respective websites. This is very important, the market penetration. So in the last couple of months, we've seen two big announcements. So Zona Space made an announcement with Trimble, and TrustPoint made an announcement with Hexagon. So Trimble and Hexagon are two of the biggest GNSS receiver manufacturers. So it's very interesting to see those market dynamics that I've mentioned. So we can see that those biggest receiver companies are already making deals with the providers that haven't launched a single operational satellite yet. So that's very impressive, and we're going to see more and more of that over the next few years. And finally, I'm going to just quickly mention the SATCOM, the communication constellations. So as I mentioned, there's many of them are going up. So Starlink is already up there, it's working, but there's many others that are going to that are just starting now. And as I mentioned, as you can see, some of them are sort of 12, 10,000 satellites, 5,000 satellites, and so on. Any one of those SATCOM companies can also do PNT should they choose to do so. And that's it. So in summary, GNSS transformed navigation some 50 years ago, but it faces growing challenges, and LEO PNT is emerging as a critical complement to enhance resilience, accuracy, security, and so on. And we can see many different initiatives going at the moment, and it's a very interesting and exciting space to watch. And that's all. Thank you very much.
Hey, great. So thank you so much, Eldar. I think very exciting kickoff presentation because we see there's so much things going on there and that we will see a major transformation of PNT with the help of LEO satellites and constellations. We received a couple of questions in the Q&A box. One was regarding slide 16. So there was the question, if you can elaborate a bit more on the ionosphere impacts on FOC. So I think this means full operation capability regarding ground station to LEO and for LEO to MEO GEO communications links. So what are the typical effects there?
Okay, sure. So If we're talking about specifically ionosphere, so because the LEO satellites are inside the ionosphere, it presents some extra challenges. So it's not just the signal that passes through the ionosphere, like with GNSS, the satellite itself is inside the ionosphere. So if there's any disturbances, it might have a bigger effect on the satellite. So satellites might get lost, or it might be disturbed. So in which case you'll need to do some more processing to eliminate the effects of the ionosphere.
Okay, I just recently add on. Okay, so FOC, so I'm on meant free space optical communications. Okay, but I think there's a couple of also books and papers on the treatment of optical kind of disturbances in those layers. Okay, then we also had another question. So why the CubeSats have lower or limited payload capacity? So can you explain this in a bit more detail?
Just simply due to size. So CubeSat is only 6U type or 12U CubeSat, 10 kilograms. So it's a very limited size, and also that will have an effect on the type of payload that you can put on that satellite. So TrustPoint is using that, the small, CubeSat. Most of the other ones are in that sort of 100 to 150 kilogram range.
Okay, great. Thank you. And then there was also one question in the chat. So please, for you, for the attendees, please note that there's difference between the Q&A box and the chat. And it's better if you use the Q&A box, but of course, we're also monitoring the chat. So in the chat, there was a question. Can you please elaborate on the current status of the sonar, those sonar constellation, particularly regarding satellite visibility?
So Zona is going to launch their first satellite in June this year. So they had a tech demo a couple of years ago, but at the moment there's no operational satellites. The first one is scheduled for June this year.
Okay, great. Thank you. So we are receiving